Hi everyone, this is Jake Fry, and today I'm going to briefly discuss integrals. So, we are in the process of trying to describe motion, and last time we figured out that the instantaneous rate of change in a vector can be found using a derivative. But what about the other way? So, for example, if we know the velocity, how can we find the total displacement over a given amount of time? So, if we have a constant rate of change, then we can use reasoning with some dimensional analysis in order to determine what the total change would be over a given amount of time. So for example, if we had the speed s of a car traveling at a constant 60 miles per hour, and we want to know how far it travels in 1 hour, and we say, distance, we can call that d, the speed, we can call it s, and our change in time is just delta t, then we would know that d would just be our speed, s, times delta t, so 60 miles per hour times 1 hour. And so we could see that the per hour unit would multiply by the hour unit and cancel out, and we would end up with just 60 miles as our answer for our total distance. And so that seems like a useful way to figure this out. But what happens if we have a variable rate of change? So can we still do that same method? Turns out we can, and we'll see why shortly. So for this, we need to instead have an idea of the inverse function of a derivative, which can be known as commonly an integral or even an antiderivative. So for a very similar case, say our speed s is 60 times t miles per hour. So in this case, our speed is a linear function with respect to time, so it's not a constant. And we want to know, again, how far we travel in that car in 1 hour. So in this case, and I'll explain all the symbols very shortly, but in this case, our distance would equal the integral, that's that curvy sign, the integrand sign, of s times dt, where dt is our infinitesimally small change in time element. And so plugging in, that would give us the integral of 60t times dt, which is just equal to 60t squared over 2, which equals 30 miles. And so we end up with something smaller than our previous example. Which kind of makes sense, I guess, because at t equals 0, we start at a velocity of 0. So we have to, take an entire hour until we get up to the same velocity that we started with the other problem. Okay, so what is, in fact, an integral? So simply put, it is the continuous analog of a sum. So what do I mean by that? So say you have a function, f of x, given by this blue curve, and you wanted to know the area under the curve. So what you could do is you could create little boxes. Since boxes are very easy to figure out what the area is, because it would just be your change in x times the height of the function. So the function evaluated at your chosen value for x. And so how you choose what your f of x value isn't all that important right now, since we're not going to do many numerical simulations of integrals. But the most important thing is that the area of a box is just length, or in this case height, times the width. And so we end up with a bunch of little boxes. And you can see, if you were to look by eye, all these blue boxes, if we're, getting a good estimate for the area under the curve. And in some cases, we're overshooting the area, in some cases undershooting. And we want to see if we can, smooth it out. So how do we smooth it out? So basically, you can imagine if we were to shrink the width of the box and increase the number of boxes until we get an infinite number of boxes, or a continuous amount of boxes, that would give us an exact value for what's under the curve. So we can see that, so for just 2 boxes, up, and then we just continue it closer and closer, we see a convergence with the more number of boxes that we use. And so if we were to take the limit such that the number of boxes approaches infinity, and then we sum over the areas of each individual box, then that function, which I guess is on the right-hand side of this equation below, would equal what we define as the integral sign from x equals a, which is our leftmost endpoint, up to x equals b, which is our rightmost, of f of x times d of x. And so you can see that the dx is the infinitesimally small version of the delta x on the right side of the equation. And we're still doing the same thing where it's finding the area of a box. So the f of x, which is the height, times d of x, which is the width. Okay, so now what are some properties of integrals? So the first property is that if you flip your endpoints, so flip from x equals b and x equals a to going from x equals a to x equals b, and you flip them, you pick up a negative sign. So just be careful if you see this. Usually that just means like if you're, checking the, I guess if you're changing your coordinate system, this will come up. Yeah. And then the next property should be relatively straightforward. So if you go from x equals a up to x equals a, that would mean your width actually has 0 width. And so if you find the area of a box with 0 width, it doesn't matter what your height is, because it will be the area equals height times width. And so width is 0. So anything that you have for height would give you 0. Okay, cool. So now the next one, basically, if you have a function and it's multiplied by a constant, you can always pull it outside of the integral. And so the way that I like to think about this is that if I have two areas that I'm summing together, and I have a common factor that's multiplying both of them, then I can always pull it out. So for example, if I have two boxes where it's, one has area equal to 2 and the other has area equal to 2, then I know that I can take out the common factor of 2. So I'd have 2 times parentheses 1 plus 1. And so then if I were to sum that together, it'd be 1 plus 1, which is 2. And so 2 times 2 is 4. And we already know 2 plus 2 is 4. So that is, the simplest version of why you can pull out this constant when you're summing together multiple things. Cool. All right. So the next property is a property that shows that an integral is a linear operation. And so what this means is if you have two functions, f of x and g of x, that are summed together, and so remember, g of x could be a negative function, so a subtraction could occur also, so you would pick up a negative sign. Just be careful with that. But, yeah, it's the same thing, addition and subtraction. So anyway, so if you have two functions that are summed together and we integrate over them, we can separately integrate the f of x function and the g of x function and then sum them together. And so you might wonder why you would want to do this. Why separate them out? Well, it can actually make it a little bit simpler in terms of remembering what an integral is for a function if it's a simpler function. So if you had a polynomial such as like x squared plus x, if you were to separate them out, then take the integral of x squared and then you add that to the integral of x, then even though it's a little bit weird because you're like, okay, well, x squared looks like a parabola and I have this extra value of x that's like slanting the parabola and I'm still trying to find the area over that composite curve. So it's a little weird, but it turns out that it works since it's a linear operation, which is great. But it's, can be kind of hard to like visualize sometimes, depending on how difficult to visualize the original function is. Cool. All right. And so now another property is that if you integrate the same function over two different regions, such that you go from x equals a to x equals c, and then you go from x equals c up to x equals b, then you could have just summed or integrated from x equals a to x equals b. And so the reason you might not realize this, but it's pretty obvious why this would occur, is that if you're continually putting up boxes up to a certain value of x under a curve, and then you just continue, it'd be the same thing as adding up the boxes from here to here. So, yeah. Okay, so now on to some important theorems in order to solve, sorry, have a cough, in order to solve problems in calculus in these definite integrals. And it's the fundamental theorem of calculus. So, the first one isn't used all that frequently, but it can be useful depending on if you're changing variables or if you have a very difficult integral that you're trying to solve. So, basically, if a function g of x equals the integral from from t equals a up to t equals x of f of t dt. So if that's true, then the g prime of x equals f of x, which means that the derivative of g of x equals f of x. Or the function g of x is defined as the antiderivative of f of x. Okay, so the far more common part of this theorem that's used in physics in order to solve the antiderivative when it's a definite function is the one below that. So basically, it's the integral from x equals a up to x equals b of f of x dx equals the antiderivative f of b minus the antiderivative f of a, where f is any antiderivative of f, of lowercase f, sorry, such that when you take the derivative of that big F, you get little f. And so basically, the more practice you have with calculating definite integrals, you'll get very used to doing this, where you find the antiderivative in general of your function f of x, and then you do the highermost endpoint first evaluated inside of that antiderivative minus the lowermost endpoint in the antiderivative. Cool. Okay, and so now here's a list of some common indefinite integrals. And so you can see a lot of them are very, they pop out for you because they look very similar to what I showed in the last lecture on the derivatives. So if you were to take on the right-hand side of the equation, if you were to take the derivative of one of those functions, then you would get what's inside of the integral without the dx multiplying factor. So each of these are indefinite integrals, and so that's why you have on the right-hand side, you're adding a constant c. Because remember, when you take the derivative of any constant, that always equals 0. And so you can't know when you do the indefinite integral what that constant is. So in a lot of times, you'll have some like starting conditions. So like if you have a velocity and you take an integral and you want to find the position, sometimes they'll give you, okay, the position started at 10 meters away from like your house. And so if you want to know how far away you got from your house in a certain amount of time, depending on your velocity, then you would just have that as an offset. So that's very common in differential equations, to always have a wide array of possible solutions when given an integral. Yeah, but yeah, these are some of the most common indefinite integrals. And I think, yeah, the only ones that are missing here that I noticed just now are logarithmic versions. So things like the integral of 1 over x would be the natural log of x. And so if you just go to the video that I made on derivatives, then you can see the opposite of whatever you get for the derivative means going the other way would be the antiderivative. Okay, and so finally, what about variable acceleration? So remember that the acceleration is the derivative of velocity. So if you wanted to know the total, say, displacement over a given amount of time, when you know this acceleration, you can you can integrate the acceleration twice. So the first integration of acceleration would just get you back to velocity. And then if you do it again, you would get to acceleration. I can't speak. You would get to displacement. And so yeah, so this is basically all that you would need to know for using integrals in order to solve equations in motion. And most often, introduction to physics doesn't even have variable acceleration, but it's useful when you have the foundation with calculus to see how you can go further into acceleration or jerk or snap, crackle, pop. You can always integrate in order to get back to higher levels. Cool, and thank you.